Okay, great. So yeah, welcome back, everybody. I wanted to start with just a really quick maybe heads up or announcement. As you might know, this Friday is a Southwestern holiday, right? And so as a result, we will not have class on Friday, right? Even though we're working remotely, we want to honor the holiday, of course. So there won't be class on Friday. And as far as the quiz goes, what I'm going to do with the quiz is I'm going to upload the quiz for a period of 48 hours. So I'm going to upload it probably later today, but it'll be open all day Thursday and all day Friday. So same as last week, if you're able to find a window of time somewhere on Thursday or Friday, and if you're observing the holiday on Friday, just be sure to do it Thursday. If that becomes an issue, of course, let me know and we'll work around it. But I just wanted to mention that. I'll send out an email that says as much later today. Otherwise, ready to get into class here. I guess before we jump into things, are there any questions about the class or about, you know, I don't know, anything at all before we get started? Any questions?
What are your office hours again?
Oh, great question. Thank you. So office hours, right? Again, office hours are happening through Discord, or at least Discord is the place to meet up with me. Sometimes if we get into the Discord office hours, I'll create a Google Meet so we can talk face to face, or I'll jump into a Zoom room or something like that. But find me in Discord during office hours. Official office hours are Monday from 3:30 to 5. Wednesday, so today, right after class, Wednesday from 9:30 to 11, and then Thursday from 1:30 to 3. So these are the same office hours that I had during the semester. I decided to keep them for a sense of continuity. But just like during the semester, I'm in my office, quote unquote, my office a lot. So I try to just linger with Discord running in the background. And so if you ever want to pop in, just jump into Discord and see if I'm there. Come say hi. So, but official office hours for today will be after this class, 9:30 to 11. Yeah, thank you. Yeah, great question. Happy to clarify. Any other questions?
Are there going to be options for extra credit if we weren't able to get the...
Yes, absolutely. Thank you, Gabrielle, for asking. I have been a little slow in getting this up and running. You might remember there were these extra credit options during the semester to go to a talk or a math event on campus and to write a short report about it. What I want to do is transition that to an online setting, and I had a couple students ask about it. I meant to do it this past weekend, and then it just got away from me. But yes, by the end of this week, let's say, I'll definitely have that up and running and send you an email about it. Instead of attending an event and writing a short report on it, I'll probably ask you to watch a certain, sort of YouTube video that I'll pick out, or a certain like sort of math related content online. So engage with this math related content and write a short report about it. So structure will be the same, just transition to an online setting. Just like before, extra credit will earn you, I think it was an additional like 1%, and you could repeat it up to 3 times for an up to 3% bump. But yes, absolutely want to keep that structure in place and embellish it. Any other questions? Yeah, great questions so far. Okay, great. Let's jump into it, and I'm going to share the screen. So last time, all right, so hopefully you can see this. Last time, or maybe I should say, for the last several classes, we have been talking a lot about power series. No, that's a lie. For the last several classes, we've been talking about series, and we've been talking about series convergence. So we've been looking at all of these examples of series, and we've been establishing a wide range of strategies for determining whether a series converges or diverges. We haven't spent as much time focusing on what the series converges to. We only really have an explicit formula for that if our series happens to be a geometric series. So we've cared less about what our series converges to, and we've cared a lot more about whether or not the series itself actually converges. And a lot of that was leading towards the object that we introduced in the videos for this class and the objects that we'll talk about today. And these are objects called power series, which, as you saw in the video, right, a power series can be thought of as an infinite expression, right? So a sum as n goes from 0 to infinity. And then depending on your notation, there is some sort of coefficient that depends on n, right? So that could be, let's say, c sub n. And then there's this polynomial looking term, which is x minus a raised to the n. Right, and so what we saw is that this a, right, that was a fixed value, some fixed number. And then the c sub n's, these were also numbers, but they depended on n, right, in the sense that c sub 0 might be different than c sub 1, might be different than c sub 2, and so on. So overall, what we get is something that kind of looks like a polynomial, but has this infinite structure to it, right? Constant out front times x minus a raised to the n. And so our what we discussed in the video is that this can be thought of as a function, right? So this can be thought of as a function, capital F of x, in the sense that I input some value x, and then I output the series c sub n times whatever that specific x value was minus a raised to the n. And then the idea was that this would either converge or diverge. This would just become a standard series. And if it happened to converge, then the number it converged to would be how we defined our f of x. So today is going to be all about practicing calculating these power series radii of convergence and interval of convergence. And so that means really that we are going to be focusing on looking at these power series and trying to figure out for which x values does the series converge or diverge. Let's jump into full screen here. Perfect. Okay, and so you've seen in the YouTube video, or I'm sorry, you've seen in the activity sheet that really the work today is just a lot of practicing determining intervals of convergence. There's a few sort of additional problems near the end that go off into different territory, but I'm gonna pick a selection of these and talk through them with you. And I'm hoping that there will be enough time today to break out into some practice, or just some breakout rooms to practice doing a few of these yourself. So I'm gonna model a handful of them, but then we'll take a look and see, we'll sort of work on them in our groups. Okay. Let's take a look at this first one to gain a sense of exactly what it is that we're thinking about here. So this is written as a series. It's a power series because it has this x value associated with it. And so it's a sum as n goes from 0 to infinity of, and it's written here in the form x to the n divided by 2 to the n. This is a power series, and I don't necessarily need to rewrite this, but I'll just point out that it explicitly has the structure we talked about on the previous page, right? So it has this structure. The coefficient could be thought of as 1 over 2 to the n, right? So that's like our c sub n. And then the piece in the parentheses is just x minus 0 raised to the nth power, right? And so our a is equal to 0 in this case. So I could explicitly rewrite this power series if I chose to in this form. And the real benefit of doing this, I'll say we don't really need to do this, but the real benefit of doing this is it explicitly highlights the fact that our power series must be centered around 0, right? We did not have an x minus a to the n. We just had an x to the n, which we interpret as an x minus 0 to the n. So in this case, this power series is centered at 0. And that will be worth remembering down the road as we construct the radius and the interval of convergence. Now, to determine the radius of convergence, I'm interested in figuring out which x values on either side of 0, which x values I can plug in here to get a series that explicitly converges, right? And so to calculate that, I need to think through my series convergence tests and apply them judiciously and critically with this extra variable x associated with it. So as long as I'm able to think through what series convergence tests apply and how the value x affects those, then I can figure out this radius of convergence. And the two tests that we'll come back to again and again and again are the geometric series test and the ratio test. The ratio test gets used a lot in power series determinings for interval of convergence. And the reason, well, we'll talk about the reason why the ratio test gets used so often down the road. So I'll remind you of that in a second. A couple of things in chat. Instead of 0, that should say centered at 0. Sorry, just my bad handwriting. I should say that this power series is centered at 0. Yeah, centered at 0. Okay, so I'm going to say geometric series test and ratio test come in again and again and again. Let's take a look in this example at the geometric series test just to verify that we can do that. So the geometric series, I could rewrite this expression. There we go. So I could rewrite this sum as the sum as n goes from 0 to infinity of not x to the n over 2 to the n, but I could rewrite this as x over 2 to the n, right? Just by condensing those exponential terms. And this is a geometric series, right? Because it is of the form sum from n equals 0 to infinity. This is of the form c times r to the n. It just so happens that in this case, the r value is this x over 2. Right, so this is a geometric series. The c value is equal to 1. The r value is equal to, let's actually be able to read that. That should be x over 2. No. There you go. It should be equal to x over 2. And so as a result, what we see is that this converges, and it converges specifically to the expression c divided by 1 minus r, aka 1 divided by 1 minus x over 2, provided that the r value is less than 1. Right, so that's something that we know about geometric series. Geometric series, I should say, that start at n equals 0 and have this form always converge to c divided by 1 minus r, provided that the r value is less than 1. And so in this case, what that means, right, sort of bringing it back up here, what that means is that we need our r value, which in this case is x over 2, we need that to be less than 1, aka we need x to be less than 2. Okay, and I should be even more careful. I should include absolute value signs on here because it's provided that the absolute value of r is less than 1. That means that the absolute value of x must be less than 2. And that actually gives me a range of x sitting between -2 and 2. Right? And so this tells us that for this power series, the radius of convergence is equal to 2. All right, and so our radius of convergence equals 2. That means that as long, and I'll say this slowly. So the radius of convergence is 2. That means, jumping back over here, we look to see where our power series was centered. It was centered at 0. And that means if it's centered at 0, I can go out 2 units in either direction, right? So that's sort of going to be my radius from the center point. So out to -2 and out to +2. And any number, any x value in between -2 and +2 that I plug in will result in a convergent series, which means that my power series will converge for those x values. Right? So if I'm trying to think of my power series as an explicit function, right? And if I'm trying to think of it as like a capital F of x, and I'm trying to figure out which x values I'm allowed to plug in, the fact that the radius of convergence is equal to 2 tells me that I can plug in any x value between -2 and 2. Okay, so we've discovered the radius of convergence. We also know, I should say this, with geometric series, we know that it converges provided that the absolute value of r is less than 1. We know that it diverges if the absolute value of r is greater than 1. But we need to explicitly check these endpoints, right? So in other words, there's this question of, I have this range right here for x values, but there's this question of whether or not these should just be strict less than signs, or whether they should be less than or equal to, right? So there's a question there of what those signs should be. And that means we have to really consider whether or not we can plug in x equals 2 or x equals -2 into our original power series. And so oftentimes when we are looking at power series and trying to discover intervals of convergence, we'll start by calculating this radius of convergence, and then we'll go in and examine the endpoints explicitly, right, as sort of 2 special cases. So let's explicitly examine as a special case the case where x is equal to +2. So if x is equal to +2, that means that I'm looking at the series, the sum as n goes from 0 to infinity, of 2 over 2 raised to the n, right? Well, that's just going to be the sum as n goes from 0 to infinity of the number 1. And that is definitely just going to go off to infinity, right? The sum as n goes from 0 to infinity of 1 to the n is just the sum of the number 1, and that will diverge. Right? And so what that means is that I cannot plug in x equals 2 into this power series and get a convergent expression, right? I cannot plug in x equals 2. And so this series is undefined at x equals 2. In other words, this inequality right here had to be a strict inequality. I couldn't plug in x equals 2 and get a meaningful answer. At the same time, let's try x equals -2. Right, so here's x equals -2. That is going to be the sum as n goes from 0 to infinity of, let's see here, we're going to end up with a -2 divided by 2 raised to the n, right? Well, that's just going to be the sum negative 2 over 2 is just negative 1. So this is just the sum as n goes from 0 to infinity of negative 1 to the n. And we've seen that's just the alternating series, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. This will also diverge, right? That sum doesn't converge to anything either. It just bounces back and forth between, I guess, 1 and 0, plus 1, minus 1, plus 1, minus 1. And so that will also diverge. And so we see then that not only is our radius of convergence 2, but I could not plug in x equals positive 2 or x equals negative 2. And so we end up being able to conclude that the interval of convergence, right, and this is going to be written in interval notation, or I'll write it in interval notation, the radius of convergence is negative 2 to plus 2, but it does not include either endpoint, right? So I'm using those soft brackets there. It doesn't include negative 2 and doesn't include positive 2. So what we have been able to conclude in this first problem is that this f of x, this power series, I should say, makes sense as an expression and is a function of the variable x and gives us an explicit number, converges to an explicit number for every x value inside this range from negative 2 to 2, but not for x equals 2, not for x equals negative 2, and not for any x value outside of that range. So that is our sort of big conclusion that we want to draw in this problem, and that's sort of the idea behind what we'll be doing for a lot of these problems. Using a convergence test, checking to see what the radius of convergence is, explicitly examining the two endpoints to see if either of them converge, and then explicitly defining the interval of convergence. So, big pause. Are there any questions about that example at the moment? Okay, all right. Let's take a look at the next one. Let's go through the next one a little bit faster. The next one is also a geometric series. It's also geometric, but I am going to approach it not using a geometric series test, but instead using the ratio test. And we'll begin to see why the ratio test will come into play so often in these power series checks. So the next one is going to be the sum as k goes from 1 to infinity of 5x raised to the kth power. So once again, this is a power series. It will be centered at 0. If I wanted to, I don't have to do this, but if I wanted to, I could rewrite it as, I could rewrite this as the sum k goes from 1 to infinity of 5 to the k times x minus 0 to the k. So that just really makes it explicit that this is a expression centered at 0 with these coefficients, these 5 to the k coefficients. So I could rewrite it like that if I chose to. So the question is, where and when does the series converge? Let's go ahead and try the ratio test this time. And so as a reminder, the ratio test said that I need to look at my expression, my a sub n. That would be, in this case, that would be this entire thing right here. So I would take that entire thing and I would calculate the n plus 1th term, I guess in this case, the k plus 1th term. So that would be 5x to the k plus 1 divided by just the kth term, so that's 5x to the k. Throw on some absolute value signs and take the limit as k goes to infinity of that expression. And then the idea was, right, just as a quick reminder, the idea was that the ratio test said this would converge if this limit, let's call it L, right? If this limit is less than 1, it would diverge if the limit is greater than 1, and it would be inconclusive. Hopefully you can still see that at the bottom of the screen, inconclusive if L equals 1. So that was what the ratio test said. So here is my limit. Let's try to compute this. And what we notice is actually that we get some excellent cancellation here. This is one of the reasons, possibly the reason, that we love, love, love the ratio test when looking at power series. When I take successive terms, I'll end up with, up here, this is like an expression involving x to the k plus 1. And down here, I get that same expression involving x raised to the kth power. And so what that ends up being, right, what that simplifies down to is simply the limit as k goes to infinity. I'm just going to end up with 5x, right? Because I have k plus 1 copies of 5x in the numerator and only k copies of 5x in the denominator, and they all end up canceling out with each other, save 1, right? So this 5k, this k in the denominator cancel out with k copies in the numerator, and so we just end up with a 5x, if you want, divided by a placeholder 1. But we end up with this 5x. And so now the question becomes, where does our original series converge? Well, according to the ratio test, right? So sort of taking this information and taking this information, this will converge if 5x in absolute value signs, 5x is less than 1, and it'll diverge if 5x is greater than 1. And this immediately gives us our radius of convergence. This is also why we love to use the ratio test, because we can interpret it really rigidly to help us determine this radius of convergence. If 5x has to be less than 1, that means that x, absolute value signs of x, will have to be less than 1/5. And therefore, we know that we are looking at x values at the moment between -1/5 and +1/5. And so that gives us a radius of convergence of 1/5. Now, we still have to check the two endpoints separately, right? We'll sort of get into the habit of checking those two endpoints separately. Okay, but at 1/5, let's see here, at x equals 1/5, we'll see something kind of similar happens down here as happened above, right? At x equals 1/5, our series becomes the sum as k goes from 1 to infinity of 5 times a fifth, so that's just 1 to the k. That's just 1 plus 1 plus 1 plus 1 forever, and that will diverge. At the same time, at x equals -1/5, what we see is we get the sum as k goes from 1 to infinity of 5 times -1/5, so that just becomes a -1 to the k. And so that's just -1 plus 1, -1 plus 1, -1 plus 1. That will also diverge, right? Because it'll just keep bouncing back and forth forever. And so what we get then, right, and I'll sort of draw my conclusion over here, my big conclusion off on the right, what we're able to conclude is that the radius of convergence, the ROC, the radius of convergence is equal to 1/5, and the interval of convergence, the IOC, is -1/5 to 1/5, not including either endpoint. Okay, so in many ways, A and B are very, very similar to each other. They're both actually geometric series. They both converge on this open interval, which is determined by the geometric series, or I should say is determined by that common ratio R. Up here, the common ratio was x over 2. Down here, the common ratio was, it was 5x. Right? In the first one, we chose to approach it from the lens of a geometric series, which means that we rewrote it in the geometric series form and knew that it converged provided that that R value, that ratio, was less than 1. And that's what gave us our radius of convergence. Down here, we chose to use the ratio test, and we ended up similarly calculating a limit that would give us the radius of convergence. So I should say we calculated the radius of convergence, but using this different test. Both have pros and cons about them. Up here, we actually found an explicit formula for what it converged to. So up here, we know not only what the interval of convergence is, but we know what it converges to. So that's kind of cool. Down here, though, we don't know what it converges to, but in some ways, this is more general. This approach, this ratio test approach, will apply to many more problems, even some that are not geometric. So once again, big pause, talk through a lot of math. Let me know if you have any questions at this moment. All right. Okay, so if there are no questions, I'm going to clear the work here. We'll move on to a new problem. All right. Let's see. Interesting. Let's jump down to D. D looks different than the one we've seen so far. It's not a geometric series. And so it will be one in which we really do want to use the ratio test. And here you'll see more examples of why the ratio test is so valuable, because we'll see more excellent things cancel. So this is a power series. For D, if we wanted to, we could rewrite it as, I could rewrite it as the sum, my coefficient out front, my piece not involving x's, that's going to be 1 over n plus 1 times 2 to the n. And then the piece involving x's, that's an x minus 4 to the n. To clarify that, it's an x minus 4. So indeed, this will be a power series that is not centered at 0 anymore. This is actually going to be centered at 4. Which means that whatever I end up calculating for my radius of convergence, that radius will be sort of stemming to either side of the number 4. 4 will be directly in the center of this, this interval we end up calculating. So this is not geometric anymore. The n plus 1 kind of throws things off, but I can still use the ratio test. And so let's see that in action. Right? So by the ratio test, we are going to take a limit that involves the n plus 1th term up top. So that's going to be x minus 4 to the n divided by n plus, I'm sorry, should be the n plus 1th term, so that should be x minus 4 to the n plus 1 divided by n plus 2 times 2 to the n plus 1. So I've just added a plus 1 to every n value. All of that divided by, let's see here, just the nth term, so that's x minus 4 to the n over n plus 1 times 2 to the n. Okay, that looks terrible. That's great though, we'll take care of this. Let's throw some absolute value signs up there. We're taking a limit as n goes to infinity. We want to figure out when that limit is less than 1 and where that's greater than 1. So the first thing we got to do, as is often the case in these ratio test expressions, is I've got to rewrite this, right? So I've got to rewrite this. I'm going to do this all in one fell swoop by taking this denominator, flipping it, and then turning it into a multiplication up here, right? So I'm going to rewrite this. Whoops, there we go. I'm going to rewrite this as the limit as n goes to infinity of This will be an x minus 4 to the n plus 1 over n plus 2 times 2 to the n plus 1 times, and here it's flipped, so we're going to end up with an n plus 1 times 2 to the n divided by x minus 4 to the n. Okay, and what we see is that a lot of great cancellation happens, as is often the case in these ratio test problems. The 2 to the n plus 1 in the denominator and the 2 to the n in the numerator, those will just about entirely cancel out, leaving us, right? So the 2 to the n will entirely cancel out, and the 2 to the n plus 1 will just be left with a 2. So we'll be left with a 2 in the denominator. Similarly, with the x minus 4 to the n will completely cancel out with the x minus 4 to the n plus 1 in the numerator, and we'll be left with a single copy of x minus 4 in the numerator. And so this whole thing radically simplifies, right? So that just becomes now the limit as n goes to infinity. We have n plus 1 in the numerator and n plus 2 in the denominator. And then we have an x minus 4 divided by 2. And the n plus 1 over n plus 2, that doesn't cancel per se, but in the limit, right, as n goes to infinity, that just goes to 1. The plus 1 and the plus 2 end up mattering less and less and less, and that goes to 1 in the limit. And so what we finally end up with is the limit as n goes to infinity of x minus 4 divided by 2. We've eliminated every n in the entire expression. So as n goes to infinity, that doesn't change. And so that's just going to be absolute value sign x minus 4 divided by 2. And that is what we want to say is less than 1. So that has to be less than 1 for our series to converge. So what does that give us? I'll start a new column here. So that gives us that x minus 4 has to be less than 2. And this will actually give us our radius of convergence, because we'll see what this means is that x minus 4 itself, without absolute value signs, has to be between plus and minus 2. I said without absolute value signs. Yeah, it has to be between plus and minus 2. And so therefore, adding 4 to everything, we'll end up with x sitting nicely between 2 and 6, right? Where I've gone from that second line to that third line just by adding 4 to every term of this inequality. So x is sitting between 2 and 6. And so what we see then is that the radius of convergence here is equal to 2. And if I were to draw this on a number line, we know that our expression is centered at 4, right? We saw over here that this power series was centered at 4. Here we have that this expression is centered at 4, and with a radius of convergence of 2, we're going all the way down to 2, and then we're going all the way up to 6. So for x values in this range, our series will actually converge. Now, we're not quite done because we still need to check and see what happens in those fringe cases. So what happens when x is equal to +4, and what happens when x is equal, I'm sorry, what happens when x is equal to +2, and what happens when x is equal to +6. In other words, we have to check these two endpoints to see whether our series converges or diverges in those cases. And as we sort of said, we want to do that in two separate pieces. So let's take a look at this. First, let's take a look at x equals 6. Let's take a look at x equals 6 first. So at x equals 6, by writing that one more time, at x equals 6, what we're going to end up with is the expression 6 minus 4 to the n, so that's 2 to the n, divided by n plus 1 times 2 to the n. And the 2 to the n's will cancel each other out, so this is nothing more than the sum starting at n equals 1. I'm sorry, starting at n equals 0 of 1 over n plus 1. And now if we think about it, this expression, when n is 0, this becomes 1 over 1. When n is 1, this becomes 1 over 2, and so on and so on. This is nothing more than our good friend, the harmonic series. Good old harmonic series. Yes. So this is the harmonic series, and because it's the harmonic series, we know that it diverges. Right? And that's it, full stop. So our power series, let's say, does not converge or is not well defined when x is equal to 6. What about when x is equal to 2? Well, when x is equal to 2, this whole thing becomes the sum of, in the numerator, we're going to have 2 minus 4 to the n, so that's negative 2 to the n, times n plus 1 times 2 to the n. Here, the negative 2 to the n and the 2 to the n don't perfectly cancel out because of the negative sign. But what this simplifies down to is actually maybe a little bit more interesting, right? This is going to become a negative 1 to the n. That's what we get when we have this cancellation between the negative 2 and the positive 2. That just becomes a negative 1 to the n. So we get a negative 1 to the n divided by n plus 1. And this is no longer the harmonic series. This is the alternating harmonic series. Right? And the alternating harmonic series actually converges. And if we don't remember that, we can use the alternating series test. Right? The individual terms are alternating. When we ignore the negative 1, they're decreasing, and they converge to 0. So this converges, and we either just remember that the alternating harmonic series converges, or we can check that it converges by the alternating series test. And so either way, what we get is the following, right? We get that the series diverges at one of its endpoints, it converges at the other endpoint, and so the interval of convergence is actually going to be from 2, including that endpoint, to 6, not including that endpoint. And I can sort of modify my picture up here. All right, so there we not only get a slightly more nuanced question than A and B, slightly more interesting example, but we get an example in which the two endpoints behave in two different ways. That really highlights, I think, the fact that we do need to check each endpoint, and we have to check each endpoint separately. All right, what do you all think? Let me know. Questions, comments, concerns?
I don't understand how when you were doing the x equals 2, how like the the 2n, you're dividing 2n over no, you're dividing negative 2n over 2n. I don't know why. I don't understand why, like, basically it cancels the 2n on the bottom but not the n on the top.
Yeah,
You know?
thank you for asking that. I appreciate that question. I think that I did a disservice by sort of scratching out the 2 and the negative 2 there. I don't think that's really explaining what it is that I tried to do there. So let me, oh no, I'm just erasing everything. Let me rewrite that, and then let me be more explicit about what it is that I did. So this was a negative 2 to the n, and down here it was a n plus 1 times positive 2 to the n. So what I really did, rather than scratch anything out, let me grab sort of a blue color here. Let me take those pieces and sort of pull them off to the side. What I have here is a negative 2 to the n over positive 2 to the n. And all I'm really doing is I'm using our rules of exponents to recognize that because the exponent is the same, I can rewrite this as negative 2 divided by 2, whole thing raised to the n. And once I do that, then I can do the negative 2 divided by 2 just inside the parentheses. And so that becomes a negative 1 to the n. So I think the scratching it out wasn't completely clear. This is really the algebra that I'm doing to simplify that down to negative 1 to the n, sort of combining all of those into a single expression, which I'm then happen to write over here in the numerator. So yeah, hopefully that helps clarify it. Let me see. Let me know if you want me to say something further, Jose, or let me know, anybody, if you have any other questions about the work that we've done here. Algebra magic, always algebra magic. Yes, exactly. Okay, great. So I'm gonna let me take a moment. It's about 8:50. Yeah, 8:51 at the moment. So I'm gonna clear this work, and then I'm going to do a quick sort of scan of the rest of the problems to make sure and see which ones I definitely want to talk about as a big group. So I'm clearing this. Okay, so a lot of these are very similar to the ones that we've already done. Let me skip ahead to talk through at least let's talk through problems 4 and 5. Yeah, let's talk through problems 4 and 5. 4 is kind of an interesting one because it ends up with so many variables floating around. It is about a sort of variation on a P series. We call it the P power series. And then problem 5 is a completely different beast altogether. So we'll talk about that as well. And then I'm actually looking at the time. That probably means we won't have time to go into breakout groups today. So I'll talk through problems 4 and 5 in nice, gory detail. And then I will be jumping down to office hours after that. So if anybody wants to keep working through problems or has questions, we can, of course, continue there. Okay, so problem 4. Show that the P power series given here for P greater than 1 has negative 1 to 1 as an interval of convergence. So let me clarify why this is called a P power series. A P series, as a reminder, I'll sort of put this in the upper right. Nope, that's the upper left. I'll put this in the upper left. A P series was a series of the form 1 over n to the P, as n went from 1 to infinity. And what we saw was that this converged for p-values bigger than 1. Okay, now that is true specifically for a p series. That's not a power series. There's no x value there. And the numerator, we notice, is equal to 1. Our p power series draws from the p series, so it still has that n to the p in the denominator, but it's in a power series form, right? So it has this, this x to the n associated with it, which we might expect from a power series. And because it has it's just an x to the n, right? We think of that as an x minus 0 to the n. And so this is a power series that is centered at 0. And so we expect the interval of convergence, right? Since it's centered at 0, just sort of taking notes up here, centered at 0. So we expect the interval of convergence to look like something of the form like negative r to r, where r is our radius of convergence. And then, of course, those endpoints will either be soft brackets or hard brackets, depending on whether or not the endpoints are actually in the interval. So that's what we expect the interval of convergence to look like. What we're claiming here is that it's specifically this. So the radius of convergence equals 1, and it includes both endpoints. And that's what we have to check. So we're assuming, I think this is sort of an interesting question because it has x's, n's, and p's all floating around. So we have to keep track of what it is we're thinking of. First, we're assuming that p is a fixed value that is bigger than 1. So I don't actually, I'm going to leave it as a p, but I'm just going to remember that my p is a fixed value and p is bigger than 1. So that being said, I still have this x, and I still need to figure out this radius of convergence, and I will try, as I tend to do with these problems, I will try using the ratio test. So the ratio test says rewrite, or I should say write the limit as n goes to infinity, and then I'm going to calculate the n plus 1th term, so that's x to the n plus 1 over n plus 1 to the p, divided by the nth term. So that's x to the n divided by n to the p. Throw on some absolute value signs and calculate that limit as n goes to infinity. So we rewrite, right? We'll do the same thing as before. Take the denominator, flip it, turn it into multiplication. This is the limit as n goes to infinity of x to the n plus 1 over n plus 1 to the p, n plus 1 raised to the p, times, and then in the numerator, over here, there will be an n to the p, and in the denominator, there will be an x to the n. Right, and then what we see is that this becomes the limit as n goes to infinity. As before, we can get some nice cancellation where the x to the n in the denominator cancels with almost all of the x's in the numerator. There's just a single copy left. And so we end up with a single x in the numerator. The n to the p and over n plus 1 to the p, that does not cancel nicely. But in the limit, that expression will just go to 1, right? You can think of it as a polynomial expression with the same constant term out front, if you'd like, or assuming that p is an integer. But because these are both sort of based with an n to the p, the lower order terms won't matter, and as n goes to infinity, this term, goes to 1. And so as a result, what we end up getting is this becomes the limit as n goes to infinity of x, full stop, absolute value of x. And that just becomes, right, because we've eliminated all of the n's, that becomes, that just becomes x. There we go. Okay, and the ratio test said that our series would converge if that limit was less than 1. So now we know that our x value must be less than 1. I'm even going to write that out in words. X must be less than 1. And so we end up with a radius of convergence that's equal to 1. And we know that our interval of convergence is something along the lines of -1 to +1, possibly including the endpoints. So we still have to check these endpoints separately. Okay, so that's where we are at the moment. Radius of convergence is equal to 1. The final thing that we have to do is we have to check these two endpoints. Let me draw a line and let's get into those two endpoints. Now, what this problem is claiming is that both endpoints are actually in the interval of convergence, right? So both endpoints are supposedly in the interval of convergence, which means that when n equals 1 and n equals -1, we're hoping that both of these converge. Let's see what happens, right? So let's start with n equals 1, or I'm sorry, with x equals 1. So if x equals 1, the series simplifies to the sum, n goes from 1 to infinity, n to the p, and then if x is 1, we just get 1 to the n, which is just 1. So the whole thing becomes the sum from 1 to infinity of 1 over n to the p. How do we know that that converges, right? How do we know that this converges? I'll put that out to you all. Okay. Yeah, so a couple answers in the chat. So it turns out this is not quite the harmonic series. The harmonic series would be if p was equal to 1 as well, and this would just be 1 over n. That would be the harmonic series. However, I think Max has it right here in the sense that the p-value is greater than 1. We had sort of assumed that. Oh, let me try doing this. This will be fun. It's not actually that fun. I'm going to highlight. Ooh, p is bigger than 1. Yeah, so because p is bigger than 1, that is the sign that we needed to see that this series converges. Because really, what we have here is nothing more than what we had originally sort of reviewed up here. This particular series converges when p is bigger than 1. And so since we're assuming p is bigger than 1, this will definitely converge. And if you were asked to justify this, like say on a quiz or something like that, you would probably say, so it converges. And then in parentheses, you could say something like p series, p bigger than 1, something like that. A great way to show that it converges. If x is equal to -1, the series simplifies to, and now it's going to be a sum, n goes from 1 to infinity. We're going to end up with an n to the p in the denominator, and we're going to end up with a -1 to the n up here. And so the question is, does that series converge? And again, I'll kick that to you all. So take 30 seconds, try to think about how you would show that that series converges. I think there are dare I say. Yes, I think there are two different ways we can show that this series converges. So see if you can come up with one of them. Take 30 seconds and take a nice long drink of water, and then we will jump back into it. All right, so yeah, I think there's a few different ways that we can see this. So Carson is saying this is an alternating series. So yes, we can use the alternating series test, and the alternating series test says that if our series is alternating, and if the positive terms, ignoring the negative one, the positive part of the term is decreasing and heading towards zero, then the series converges. So yes, by the alternating series test, this converges. Alternatively, a fun thing we can do is we can try to show that this series converges absolutely, right? Because if I threw on absolute value signs, I would get kicked up to this setting, which I've already seen definitely converges, right? So I could either say this converges by the alternating series test, or I could say this converges because it converges absolutely, because when I throw on absolute value signs, I get a p series where p is bigger than 1. So yes, our two different methods for showing this, that this converges. Again, if this was a quiz and you were asked to justify this, to sort of explain your reasoning, I would love to see something along the lines of converges. I would love for you to say alternating series test if you were using the alternating series test. And then you could say 1 over n to the p is decreasing and converges to 0. Right, because those were the two conditions that you had to check for the alternating series test. Okay, and I think that's a complete picture of this problem. We found the radius of convergence, we saw that it went from -1 to 1, and then we explicitly checked both endpoints. An interesting question, which is not asked on this activity sheet, but I encourage you, especially if you're in Central Texas and the weather is really nice today, find some time, sit outside, grab a cup of coffee or something, and just sort of mull this over. What would happen if p was not greater than 1? So let's say if p was 1/2, how would that change this problem, right? If p was equal to 1/2, would the interval of convergence change? Would the endpoints change? What would change in that situation? I think that's an interesting question. Okay, that being said though, we've got about 8 minutes left, 8 minutes everyone, and I want to talk about this final problem because it is a different kind of beast than the others on this sheet. This problem sort of goes in the other direction. So far we've been looking at power series and we've talked about radii of convergence. Yeah, we've talked about radii of convergence for power series and how they might represent functions, these capital F of X's. Here I'm given an explicit function, the function arctangent of x over 3, and we want to determine radius of convergence for a power series that describes this function. So that's not easy to do. And so I want to spend the rest of the class talking about this. Now, we saw a little bit of this in the second video for today, but an important jumping off point that we have is that certain power series functions can be thought of in certain nice forms, right? Or we can write them in nicer forms. What I mean by this is we saw in our video that if I have a function, power series function from n equals 0 to infinity, of c times r to the n, this was our geometric series, that is a function, that's a capital F of x as n, as long as, well, let me actually say, instead of r to the n, let me say x to the n, right? That's a power series as long as our x value is less than 1 in absolute value. But we also saw that I could write this in the form 1 over 1 minus x. This is because for geometric series, I have an explicit formula for what my geometric series converges to, right? Geometric series at this moment in time are the only series where we have such a formula, right? So not only do I have this power series representation, but I happen to know what it converges to. And so let me rewrite that in sort of a less convoluted way. Let me write that as the sum, n goes from 0 to infinity. I'm literally just rewriting it. I should say in this case, actually, our c value is just equal to 1, because normally we would have a 1 up front. So the sum as n goes from 0 to infinity of x to the n is equal to 1 over 1 minus x. Okay, great. And what we saw in our video is that we can actually use this expression to calculate new power series representing new functions, right? So for example, we could take the derivative of the thing on the right-hand side, we would get a new function over there, and we could take the derivative of the thing on the left-hand side, right? And what we saw in the video is that to take the derivative of this expression, we would need to calculate, that derivative piece by piece. And so taking that derivative would result in something like this, right? If I took the derivative on the left-hand side and I took the derivative on the right-hand side, we would end up with new expressions. For example, on the right, we would end up with negative 1 over 1 minus x squared times the derivative of 1 minus x squared. So that would become a positive 1. And on the right, we would end up with the sum as n goes from 0 to infinity of n times x to the n minus 1, like that. And now our goal, and so I should say, in this case, we now have a new function with a power series representation. So the goal of this problem, and I worry I might not quite have time to finish it, but the goal of this problem is to try to use these kind of manipulations to develop a power series formulation for the arctangent function of x over 3. And now to do this, this is actually very tricky. We need to come up with a nice way to get to the arctangent function using expressions that kind of look like this or kind of look like this, sort of using our jumping off point. And so in my scratch work, let me call this scratch work, and green will be the color for scratch work. So for scratch work, I want to think about the arctangent function. So the arctangent function of x over 3, if I were to take the derivative of that, right? So if I were to take the derivative of the arctangent function, well, the derivative of arctangent is 1 over 1 plus x squared. And so the derivative of arctangent of x over 3 by the chain rule will be 1 over 1 plus x over 3 squared times the derivative of x over 3. Right? And so we end up with that expression, 1/3 over 1 plus x squared over 9. And this, at least theoretically, has a similar structure to this. Right? There's a few things that are different. There's this minus sign instead of a plus. There's this x instead of an x squared. And there's this divided by 9 instead of, I guess there's nothing. So there's a lot of different things, but at least structurally, they look kind of similar. And so now the question is, how can I manipulate this to in turn manipulate this to get that to look more like this? Because thinking through this, if I can manipulate this series, which will in turn manipulate this, to make it look like this, then I can simply integrate to get the arctangent function. And that's going to be sort of my approach here. Now, let's see. Oh man, we're completely out of time. I was going to say, let's see how far we can get. We're not going to be able to get anywhere. Let me at least hint in the right direction. And then this is something that you can continue based on the video and based on what we're saying here. One thing that we can do, I guess this is still scratch work. We originally had 1 over 1 minus x equals the sum, as n goes from 0 to infinity, of x to the n. But this is true no matter what I plug in for x. Right? So in other words, I can replace that x with an expression involving x, and this would still be true. So what if instead of x, I replaced it with x squared? So let me quickly rewrite that. Instead of x to the n, what if I ended up with x squared to the n? Well, that would mean that I would get an additional x squared right here. And what if I didn't have it as x squared to the n? What if the thing in the parentheses involved a negative sign? What if it was negative x squared to the n? Well, then the thing here, this would become a minus negative x squared. And I've built up an expression now that begins to look like 1 over 1 plus x squared. And I'm well on my way towards getting something that looks like this. Now, I want to be conscious of time, so I want to be able to let you go. I know some of you have other places to be, but this gives us a new way to think about manipulation of power series that was discussed in the video, that was discussed a little bit here, and that we can continue talking about going forward. Let me stop the recording there, and let me say have an absolutely wonderful rest of your day. If you want to talk a little more about this problem or others, I will be in Discord for my office hours here in a moment. And because it's a holiday on Friday, keep an eye out on Moodle for the quiz that's going to be up tomorrow. Have a great rest of your day. Have a great weekend, and I will see you all on Monday.